Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Have you ever looked up at the night sky and just wondered what secrets our own galaxy, the Milky Way, truly holds? I mean, it really holds. What if I told you there's this invisible cosmic fog out there, and it's hiding some of its biggest mysteries, but a new mission is about to cut right through it. Give us a view we've, only dreamed of. Today, we're really getting into the ambitious journey of NASA's Nancy Grace Roman Space Telescope. And look, this isn't just another launch, It's a mission specifically designed to reveal our home galaxy through the very stuff that's always hidden it. Cosmic dust. We're talking about an unprecedented exploration, how Roman will use this seemingly everyday material, cosmic dust, to paint a three-dimensional picture of the Milky Way, something far beyond anything we've managed before. You've shared some really fascinating material from NASA's Goddard Space Flight Center, really digging into Roman's capabilities at its Galactic Plane Survey. Our goal today is to unpack the most exciting parts of this whole thing. We want you to understand not just what Roman will do, but why it matters so much to us right here on Earth, and what incredible insights it might unlock about, our cosmic neighborhood.
It really is an exciting prospect. Because Roman, it isn't just another telescope we're adding to the collection. It's specifically engineered, really designed, to tackle this fundamental, long-standing challenge in astronomy. Seeing through that obscuring dust that has always shaped and honestly limited our view of the galaxy. For decades, we've been piecing together clues, hints. But the true structure, the architecture of our home galaxy, it's remained shrouded. And this raises a huge question for all of us, doesn't it? Just how much more about our own galaxy have we been missing all this time?
Yeah.
And what might that unseen picture actually reveal?
That really is the crux of it, yeah. And this leads us right into understanding that, the invisible fabric of our galaxy, what scientists call the interstellar medium, or the ISM. You see, when you look out at the vastness between the stars, and there are more than 100 billion stars in the Milky Way, those spaces, they aren't empty, even though, they look that way to our eyes.
Exactly. They're filled with this diffuse but incredibly important stuff, the interstellar medium. It's mostly gas, hydrogen, and helium. Mainly the most common stuff in the universe.
Mm-hmm.
But crucially, it also contains these tiny solid particles. Dust.
Mm-hmm. Dust.
And while the gas makes up most of the mass, it's often this dust that plays the really intriguing and, let's be honest, for astronomers, the most frustrating role. This cosmic dust, even though it seems so sparse, it's incredibly good at blocking our view.
And that's the paradox, isn't it? This dust, which is so good at hiding things from us, it's also deeply connected to the cycles of life and death in the galaxy.
Absolutely. What's truly fascinating is its dual nature. It's simultaneously the raw material, you could say the seeds of new stars,
okay.
And at the same time, it's the remnants, the leftover crumbs from stars long dead.
Oh, okay.
So you have this incredible continuous galactic recycling system going on. Think of it like a cosmic circular economy, maybe, where the building blocks for new stars, new planets are constantly being made from the ashes of old ones. It's this grand cycle that keeps renewing the galaxy.
That cosmic recycling idea, that really clicks. But while this dual role is obviously vital for how galaxies evolve, for us trying to see things from inside the galaxy, this seemingly thin dust is just a massive challenge. It's like if you were trying to map a dense forest, right? But every time you tried to look far ahead, this thick, constant fog rolled in. That's basically the problem astronomers have.
Mm-hmm.
These dust clouds make it incredibly difficult to map the fine details of our galaxy, especially when we try to look, say, towards the other side from where we are. It's like having this huge galactic blind spot stretching tens of thousands of light years across. Large parts of our own home are still a mystery.
Exactly. Imagine trying to get a clear picture of a whole city, but you're standing right in the middle of its downtown square. And all the distant buildings, the suburbs, they're just covered in this constant smog.
Yeah.
You can see the nearby stuff, okay, the immediate structures, but anything further out just gets blurry, indistinct, or totally hidden. That's our situation in the Milky Way. We're embedded right inside the disk of our own spiral galaxy and the dust. It's particularly thick in that galactic plane.
Right where we live.
Right where we live. So while we can see nearby stars and structures pretty clearly, our view gets incredibly blocked and distorted the moment we try to peer through those denser regions or just further away.
And this limitation has meant that, for ages, scientists have been trying to piece together what the Milky Way likely looks like using a sort of cosmic guesswork. They combine the observations we can make nearby with what they see in other spiral galaxies we see from the outside, edge on or face on.
Looking at analogs.
Exactly. They guess what our galaxy probably looks like based on these distant cosmic cousins. It's an educated guess, for sure, a very educated one, but it's still like an artist's impression when what we really want is the architect's blueprint, you know? We're trying to understand the whole house, but we're stuck in one room, and all the windows are just covered in dust.
It's a frustrating perspective sometimes.
So how do we ever hope to map our own galaxy properly when we're looking through this constant cosmic haze? This is exactly where the Nancy Grace Roman Space Telescope comes in. It offers this truly breakthrough vision, promising to just slice right through that cosmic fog. And Roman's big innovation here is harnessing the power of infrared light. Now, for anyone not familiar, infrared light is basically light with longer wavelengths than our eyes can see. It sits just beyond the red end of the visible spectrum that we perceive. We can't see it directly, but it carries a ton of information about the universe, especially when visible light gets blocked.
And the real genius of using infrared lies in how it physically interacts, or rather, doesn't interact as much, with cosmic dust. The longer the wavelengths of light, the more likely it is to just pass right through a dust cloud without getting scattered all over the place like visible light does.
Okay, so longer waves just push through better.
Sort of. Think of it like this. Imagine tiny ripples on a pond hitting a small pebble. Those short, choppy ripples. They'll break up, scatter quite a bit. But now imagine a long, rolling ocean wave hitting that same pebble. It might pass right over it, relatively undisturbed, right?
Right, I can picture that.
Visible light, especially the bluer, shorter wavelengths, acts more like those choppy ripples when it hits typical dust grains. It scatters easily. And that's why dust clouds look dark and opaque to our regular telescopes. They're blocking and scattering the light coming from behind them.
That's a great way to put it. So the shorter wavelengths, like the blue light from hot young stars, those are the choppy waves. This blue light more easily scatters, as the material says, when it hits the dust. And that scattering effect is why those dust clouds look so dark in visible light pictures, that they're just soaking up or bouncing away that light.
And this scattering leads to a really crucial effect, something Roman will really exploit. Stars shining through dust appear dimmer and redder than they actually are.
Ah, okay, redder.
Yeah, redder. The blue light from the star gets scattered away much more effectively by the dust, leaving mostly the redder, longer wavelengths to actually reach our telescopes. This reddening isn't just, a color change. It's a direct signature. It tells us the dust is there and gives us clues about its properties.
Like looking at a sunset through our own atmosphere.
Exactly like that. The blue light gets scattered away by the air molecules, leaving the sun looking orange and red. Roman, by observing across a whole range of infrared wavelengths, can measure precisely how much the light is reddened in each different infrared band. And that acts like a unique fingerprint, telling us about the specific sizes and maybe even the composition of the dust in that direction. It basically gives us a window through the haze.
So it's not just about seeing through the dust, but actually reading the dust itself, deciphering its properties based on how it changes the light.
Precisely. That's the really clever part.
And that's where this mission gets even more exciting, right? Unlocking the dust's own characteristics and then using that info to build these incredibly detailed 3D maps of our galaxy.
So the basic technique, as I understand it, involves astronomers comparing Roman's infrared observations with what they already know, or can model, about the star itself, its intrinsic characteristics.
Right. We have pretty good models and observations from other surveys that tell us a lot about how bright a star should be, what its color should be based on its type, its temperature, its age, that kind of thing.
Okay, so you have a baseline.
Exactly, a baseline. Then, by measuring exactly how that star's light has been changed by the dust, it traveled through how much dimmer it is, how much redder it is across those different infrared wavelengths, astronomers can start to untangle that data. The critical goal, as the NASA material puts it, is to disentangle the star's distance from how much its colors have been reddened.
Which sounds tricky because a star could look dim just because it's really far away, right? Or because there's a lot of dust in the way. That's the challenge. But by using Roman's multi-wavelength infrared data and combining it with our knowledge of the star's inherent properties, maybe from looking at its spectrum, which tells you its type, and thus its true brightness, they can separate those two effects. This lets them figure out the specific properties of the dust itself, giving us a much clearer, much more accurate picture of how the dust is distributed.
Okay, got it.
And this is where the details get really powerful. Brandon Hensley, a scientist studying interstellar dust, explains it really well. He points out that by asking, how much redder and dimmer is the starlight that Roman detects at different wavelengths, across its different filters, we can then take that information and relate it directly back to the properties of the dust grains themselves, and in particular, their size.
Their size, wow.
Yeah, their size. This is a critical insight. Think about trying to figure out what's in a fog bank without actually touching it. Different sized dust grains, tiny smoke-like particles versus larger pollen-like grains. They affect light in slightly different ways. By analyzing how much reddening happens at each of Roman's infrared wavelengths, scientists can actually deduce the average size of the dust grains in that specific direction. It's incredible detail about the very fabric of the ISM.
That's amazing. And it goes beyond just size, too.
Oh, yeah. The insights go well beyond just particle size.
Yeah.
Scientists will also learn about the dust's chemical makeup. Is it mostly silicates, like tiny grains of sand? Or is it carbonaceous stuff, more like soda or graphite? Each composition interacts with infrared light a bit differently, leaving its own subtle signature. And even more than that, they'll be able to investigate the physical processes behind changing dust properties. So how does dust evolve over time? How is it made by dying stars, maybe destroyed by supernova shockwaves, or changed as it floats around in the galaxy? These are the fundamental details we need to really understand the raw material of our galaxy and really all galaxies.
Okay, now here's where it gets really interesting. I mean, this sounds like a genuine paradigm shift. By collecting all this incredibly fine-grained information, the reddening, the dimming, the dust grain size, the composition from literally, as the source says, billions and billions more stars. Astronomers can then piece together all these individual data points like a giant cosmic pointillist painting. And this incredible feat will let them construct detailed 3D dust maps of the Milky Way. Just think about that for a second. Not just a flat picture, but a truly volumetric understanding of where the dust is, how dense it is, what it's made of, how it varies throughout huge regions of our galaxy.
It's like going from looking at a 2D photograph to having a fully explorable holographic model. It's that kind of leap.
Exactly. A hologram of the Milky Way's dust.
And this leads directly to what Catherine Zucker, an astrophysicist involved in this, described as a total game changer. These maps will enable scientists to create a model of the Milky Way, which will show us how it looks from the outside.
From the outside, that's the dream, isn't it?
It really is. This is a critical leap because for the first time, we'll have a data-driven blueprint of our own galaxy. Imagine being able to actually see our entire galactic home, its spiral arms, its central bar, its dusty lanes, all laid out in front of us as if we were looking at it from, say, the Andromeda Galaxy.
Wow.
This kind of clarity will finally let us properly compare the Milky Way with all those other galaxies we only ever see from afar. It helps us, as Zucker says, slot it into a cosmological perspective of galaxy evolution. It's incredibly hard to figure out your place in the grand scheme of things if you don't even have a clear picture of your own home.
And the sheer ambition, the scale of this whole thing, it's just mind-boggling, frankly. Catherine Zucker really emphasized that Roman will add a whole new dimension to our understanding of the galaxy because we'll see billions and billions more stars.
Billions. With a B.
Billions. And it's crucial to remember this isn't just about counting stars like notches on a belt. It's about the treasure trove of information each one carries. She points out that the dust data is encoded in every star Roman detects.
Right.
So every single star Roman looks at becomes like a tiny cosmic probe telling us something about the interstellar stuff its light passed through on the way here.
Yeah, like having billions of tiny flashlights shining through the fog.
Exactly. Each one revealing a little bit about the fog's density, its composition, its properties right along that line of sight. This isn't just a survey. It's like a galactic census on an absolutely unimaginable scale. It's going to give us an unprecedented volume of data.
And building on that incredible scale, this interstellar medium, this dust and gas, it does so much more than just get in our way, right? It's intimately involved in those fundamental galactic life cycles we mentioned earlier.
Right, the recycling.
Recycling, yes.
Yeah.
The ISM fuels star and planet formation. It's not just passive stuff floating around, it's the active ingredient, the cosmic clay, used to create everything we see. It truly is the architect of stars and worlds.
So how does that process work, starting from the ISM?
Well, it generally starts when dense blobs of interstellar medium-form molecular clouds. These are often very cold, very dark regions where the gas and dust get concentrated enough, dense enough to start collapsing under their own gravity. They overcome the internal pressure pushing outward.
Okay, so gravity takes over.
Gravity takes over. Inside these clouds, even small variations in density can cause regions to become even denser. And these denser clumps then gravitationally collapse and kick off the first stages of star development. Think of it like a cosmic whirlpool starting up, spinning faster, pulling in more and more material as it collapses inward. Eventually, the core gets so hot and dense that nuclear fusion ignites, and boom, you have a new star.
Wow, and that takes millions of years.
Millions of years. Yeah, it's not quick. Right. But Roman will give us these amazing snapshots of these stellar nurseries all across our galaxy, even the ones hidden behind thick dust.
And the cycle doesn't just stop when the star is born, right? The dust keeps playing a role.
Not at all. Once these young stars ignite, they're not just passive endpoints. They actively influence their surroundings and contribute to the ongoing cycle. These young stars eject hot winds, powerful outflows of particles and radiation. And these winds can cause surrounding dust to clump into planetary building blocks.
Ah, so the star itself helps build its own planets.
In a way, yes. It's a crucial link. It shows how cosmic dust isn't just floating randomly. It's actively participating in building bigger things. These dust grains made of silicates, carbons maybe coated in ice, they start colliding and sticking together in the swirling disk of material around the young star. They grow from microscopic specks into pebbles, then into kilometer-sized planetesimals, and eventually these can smash together and grow into entire planets. It's the grand cosmic assembly line, turning diffuse dust into solid worlds like ours.
So, okay, bringing it back, what does all this mean for us? For you listening, for us as people living on Earth? It connects directly to our own cosmic origins, doesn't it? We hear we're made of stardust all the time, but this makes it feel much more tangible.
It really does. Josh Peak, an associate astronomer at the Space Telescope Science Institute, has this really powerful way of putting it that it clicks. He says dust carries a lot of information about our origins and how everything came to be.
Okay.
And then he gives this incredibly relatable aha moment. Right now, we're basically standing on a really large dust grain. He says, Earth was built out of lots and lots of really tiny grains that grew together into a giant ball.
That's incredible when you think about it like that.
Isn't it? Just pause on that for a second. Every single atom in your body, every rock, every ocean on Earth, its history traces back to these tiny dust grains, grains which themselves were forged in the hearts of stars that died long ago. It really does change how you think about the ground under your feet. It makes you feel profoundly connected to the cosmos.
Honestly, that gives me chills. Oh, wow. And Roman's mission, it's going to elaborate on these galactic life cycles even more by mapping these star factories across the galaxy with way more detail than before. It's set to identify young clusters of stars in new, distant star-forming regions. These are the busy nurseries where new generations of stars are being born right now, often hidden behind those thick dust curtains. Pinpointing these nurseries, understanding exactly where they are and what the dust around them is like. That helps us understand where and how the galaxy is actively building new things.
It's like taking a detailed census of all the active construction zones in our galactic city.
Yeah, that's a good way to think about it.
And crucially, this isn't happening in a vacuum. Roman is very much building on the legacy of previous missions, building on their foundational work. It will contribute data on star factories previously identified by missions like NASA's retired Spitzer Space Telescope.
Ah, Spitzer. A legendary mission.
Absolutely. Spitzer was a real pioneer in infrared astronomy. It gave us these incredible, though often more limited glimpses into these dusty star-forming regions. Roman will essentially pick up where Spitzer left off, but provide a much, much wider view, a deeper view, and with more detail across the entire galactic plane.
So it's like Spitzer gave us intriguing close-ups of a few construction sites.
Exactly. And Roman is going to give us the full, wide-angle, high-definition panorama of all the active developments happening at once. It shows this beautiful continuity in science, doesn't it? Leveraging past discoveries to enable the next big breakthroughs.
It really does. And connecting all this together, Katherine Zucker emphasizes how vital it is to truly understand the environment where stars form. She says, if you want to understand star formation in different environments, you have to understand the interstellar landscape that seeds it. Makes sense.
It does.
And Roman will be able to link the 3D structure of the interstellar medium with the 3D distribution of young stars across the galaxy's disk. which means we won't just see where stars are forming anymore. We'll also understand the specific properties of the gas and dust right there, the density, the composition, the motion that allowed those stars to form in the first place.
It's about seeing the whole ecosystem, isn't it? The cause and the effect all laid out in 3 dimensions. This could genuinely revolutionize how we understand the way galaxies manage their star formation over cosmic time.
Okay, so beyond individual stars and where they're born, Roman's insights are also going to help us untangle some of the Milky Way's really big structural mysteries, particularly the puzzle of its spiral structure. You know, that classic pinwheel-like pattern we see in pictures of other galaxies?
The iconic spirals.
Where stars, gas, and dust bunch up like galactic traffic jams. Our own Milky Way has these beautiful, grand spiral arms, but exactly how they work, where they came from, what they do, that's still a bit fuzzy for astronomers.
Indeed. And if we connect this back to the bigger picture, the overall architecture of the galaxy, Roman's new 3D dust maps are going to be absolutely critical. They'll help refine our understanding of this spiral structure immensely. Right now we have general ideas, models, but these maps will provide unprecedented detail about where the dense material, the dust, is actually concentrated within those arms. And crucially, how that concentration relates to where the stars are, where the gas is.
It's like finally getting a clear, high-res satellite view of a really complex highway system instead of just blurry aerial photos from miles up.
Exactly. We'll be able to see the specific lanes, the on-ramps, the congestion points of our galactic traffic much more clearly.
And the actual cause of the spiral structure itself is still debated, right?
That's right. The precise cause is currently unclear, as the material notes. There are a few leading theories. One popular idea involves density waves sweeping through the galactic disk, kind of like ripples, that temporarily compress the gas and dust as they pass.
So not physical waves crashing, but more like traffic jams.
Exactly. That's a good analogy. It's not like the material itself is crashing, but more like a persistent traffic jam on a highway. Individual cars or stars and gas clouds, in this case, are constantly moving into and out of the slowdown zone, the jam. But the jam itself, that region of compressed, slowed down traffic, persists and moves along the galactic disk.
Okay.
Other theories involve things like gravitational nudges from nearby satellite galaxies or instabilities within the disk itself. Roman will help figure this out by combining velocity data with dust maps.
Velocity data, how things are moving.
Exactly. That tells us how the stars and gas are actually moving within and around the spiral arms. By seeing how stuff is moving and then correlating that with a detailed 3D map of where the dust is thickest, scientists can compare observations with predictions from models to help identify the cause.
So they can test the theories.
Precisely. They can rigorously test those competing theories against real, high-resolution data. Are the arms relatively stable, long-lasting structures? Or are they more temporary, constantly forming and dissolving? Roman will give us crucial, maybe even definitive clues.
And the role these spiral arms play in forming stars is also still debated. It feels like there's a lot we don't know about our own galactic neighborhood.
There really is. It's almost a cosmic chicken and egg question.
Yeah.
Some theories suggest that these galactic congestion zones, these traffic jams where gas and dust pile up, directly trigger star formation.
Yeah.
The compression itself could be the spark that causes gas clouds to collapse.
Okay, that makes intuitive sense. Squeeze stuff together, it makes stars.
Right. But then other theories argue that these traffic jams mainly just gather material. They act like cosmic conveyor belts or storage bins, bringing the raw ingredients together. But they don't necessarily stimulate new star birth directly. Maybe something else triggers it once the material is gathered there.
Okay. A subtle difference, but important.
It's a subtle but really significant distinction, yeah. And it has big implications for how we understand galactic evolution and how star formation works across the universe.
So how does Roman help settle that debate?
Well, this is where Roman's huge data set becomes absolutely invaluable. By providing more data on dusty regions across the entire Milky Way, especially right within the spiral arms themselves, Roman will let scientists compare many galactic environments and study star birth in specific structures, like the galaxy's winding spiral arms or its central stellar bar.
So they can compare star formation inside an arm versus just outside it.
Exactly. They can compare rates.
Yeah.
Look at star formation rates inside a spiral arm versus just outside it, or in regions with really dense dust versus less dense regions, and then compare those observed rates to what the different theories predict should happen. This kind of comparative analysis across the entire galactic disk, with a 3D view of both the dust and the young stars, that's something we just haven't been able to do with this kind of statistical power before. It offers a real chance to finally answer these long-standing questions about what really really drive star birth in galaxies like ours.
This whole mission truly represents a legacy, doesn't it? Not just for the scientists working on it now, but for future generations, for all of us who look up at the sky.
Absolutely.
The sheer scale of what Roman is expected to achieve is it's almost hard to grasp. Its Galactic Plane Survey is planned to map roughly 20 billion stars.
20 billion.
That's about 4 times more stars than have currently been mapped by previous surveys like Gaia. It's a staggering leap in just mapping our home galaxy.
It really is.
We're talking about an unprecedented data set that's going to reshape galactic astronomy for decades. It'll offer insights we probably haven't even thought to look for yet.
Josh Peak really captured the magnitude of this when he said, with Roman's massive survey of the galactic plane, we'll be able to have this deep technical understanding of our galaxy. It's not just a surface-level map. It's a deep, granular understanding, its components, how they move, its history, its future potential.
Yeah.
And this isn't just data for today's researchers. It's a foundational data set. It's going to power discoveries for generations, much like, the Hubble deep fields are still yielding new science decades later.
And what's truly exciting, especially in this day and age, is how accessible this data will be. It feels like a real scientific gift to the world. After the initial processing, Roman's data will be available to the public online, specifically through the Roman Research Nexus and the Barbara A. Mikulski Archive for Space Telescopes, or MAS.
Right. MAS already holds data from Hubble, TESS, JWST.
Exactly. And these aren't some obscure locked-down archives. These platforms will each provide open access to the data for years to come.
Which is huge.
It means anyone, professional astrophysicists, curious university students, even dedicated citizen scientists working from home will be able to dive in, explore, and analyze this incredible wealth of information. The potential for discovery by people outside the usual channels is just immense.
That open access really fosters a more collaborative, a more expansive scientific future. It helps democratize discovery, doesn't it?
It really does.
Josh Peak's vision for the future here really sums it up perfectly. He said, people who aren't born yet are going to be able to do really cool analyses of this data.
Wow. People who aren't born yet.
Yeah. Think about that. It frames Roman's mission as something much bigger than just an immediate scientific return. He called it a really beautiful piece of our heritage to hand down to future generations and to celebrate.
A piece of our heritage. I like that.
It's providing the tools, the raw material for discoveries we can't even imagine right now. It ensures the legacy of this mission will just keep unfolding and inspiring for decades, maybe even centuries.
So for everyone listening who's now eagerly anticipating this, when can we expect Roman to actually launch and start this incredible journey?
Well, the official plan is for Roman to launch no later than May 2027.
Okay, so within the next few years.
Yes, but the team is actually working towards a potential early launch, possibly as soon as fall 2026.
Oh, even sooner. That's exciting.
It is. So the wait might not be too much longer until we start getting these unprecedented insights and quite literally these new pictures of our home, the Milky Way.
Okay, so just to kind of wrap up everything we've talked about, the Nancy Grace Roman Space Telescope is really set to revolutionize how we see and understand the Milky Way. It's going to do this by peering straight through that cosmic dust that has hidden so many secrets for so long. It basically turns an obstacle into an amazing tool. Using its incredible infrared vision, Roman won't just see through the interstellar fog, it's going to decode the fog itself, its properties. That will let us build the most detailed 3D maps of our galaxy ever created.
Yeah, truly three-dimensional.
And these maps promise to unlock fundamental mysteries about how stars and planets form, shining a light on our own cosmic origins. And they'll help us finally figure out the causes and the roles of the Milky Way's beautiful but still mysterious spiral arms.
Which really raises a final thought, maybe, for you listening. As we gather all this unprecedented data about our galaxy's structure, its origins, as we push the boundaries of what we can see and comprehend, how might our own understanding of humanity's place in this vast cosmos continue to shift and expand?
That's a big question.
It is, because it's not just about distant stars and dust clouds, is it? It's fundamentally about our story, our origins, written in the very fabric of the universe, and how deeply connected we are to all of it.
Absolutely. So the next time you look up at that shimmering band of light we call the Milky Way, just remember, it isn't only a collection of faraway stars. It's this vast, dynamic, living system where cosmic dust, the seemingly simple stuff, holds the keys to understanding our past, our present, and maybe even our future. What incredible new views will Roman unlock for us? And how will those revelations change the way we see ourselves within this magnificent cosmic dance?
Only time. And that penetrating gaze of infrared light will really tell.